In the previous lecture, we have seen the equation of illumination that we are building. One is the Ke lambda, which is the intrinsic property of the object being illuminant or being a light source. The object is itself a light source, and the second term is the ambient light source, which depend on the property of the object, which is Ka lambda, and the second one is the ambient intensity, which is there in the room due to scattering from different walls or being light reaching from neighboring rooms or from sunlight leaking through the edges of the window. We now continue with development of the equation of light or the illumination equation, which we will use in graphics. Model surface reflectance. Now, if I have a surface and I have an incident beam of wavelength lambda hitting at an angle, the spherical angle of theta phi using spherical coordinates, it reflects at an angle xi lambda. Now this reflection follows the laws of reflection of physics. Basically, if I draw the normal to this surface, the angle of incident will be the angle of reflectant. So now let us continue further in generating the empirical model. Ideal measure radiant energy for all combinations of incident light. It requires too much of storage and difficult in practice. And therefore, let us take physics of reflection. The ideal diffuse reflection, an ideal diffuse reflector at a microscopic level is a very rough surface, real world example chalk. Because of these macroscopic variation, an incoming ray of light is equally likely to be reflected in any direction over the hemisphere. What does the reflected intensity depend on? So what you have is that a light ray hitting a surface gets uniformly reflected in all directions. The only thing that it depends on is the direction in which there is this incident beam. Now it has been observed if the incident beam is perpendicular to the surface, that is, it makes an angle of 0 with the normal to the surface, the intensity of this scattered radiation is maximum, while it is minimum when this incident beam is at 90 degrees to the normal to the surface. So let us see the relationship, the diffuse reflection. How much light is reflected depends on the angle of incident. So here I have the normal to the surface, and the surface is being illuminated at an angle theta. So what is a normal? We have seen the normal of a surface. The surface, any spherical surface also could be broken up by tangential surface, which could give me normals. And these normals can be calculated by the coefficients of the surface equation, ABC being the first three coefficient of the surface equation, which gives the coefficient of the normal. Now please note is that we cannot generate the normal with the surfaces we generate and transform it using our transformation, because the normal will not remain normal as you do this transformation. As you see in this example, normal which is there in the first figure, due to anisotropic scaling, the normal no more remains a normal. And therefore, it is always better to compute the normal on the fly by knowing the equation of the surface, or knowing 3 points on the surface from where you could generate the equation of the surface, and the coefficient of the equation of the surface will always provide us the direction of the normal. So direction of light source. For a directional light source, we make a simplifying assumption. The direction is constant for all surfaces in the scene. All rays of light from the source are parallel. To begin with, let us assume parallel rays hitting the surface, as if the source were at infinity, far away from the surface in the scene. A good approximation for the sunlight. But of course, the light sources, indoor light sources, certainly are not, are at a particular direction, and they are radially diverging rays which hit the surface. But to begin with, let us assume that the light source hitting the object is all coming parallel to the surface. The direction from a surface to the light source is important in the lighting the surface. Now, since the rays are coming parallel, there is a single direction or a single angle theta in which the light source are hitting the surface, the angle theta being the angle of the incident beam to the normal of the surface. So here you have the parallel rays hitting the surface of. Now let us assume a diffuse reflection. How much light does it reflect depends on the angle of incident light. So what you see is that we have a beam of light, of a beam which has a diameter, an area of dA naught. Now, due to this angle theta, this beam is spread over an area which is dA. So if we write the equation, the intensity which was over a smaller area dA naught is spread over a larger area which is dA, and the equation relating dA naught with dA is cos dA cos theta. D naught is equal to dA cos theta. Now, assuming the conservation of energy, we can see that the beam basically having an intensity, density over multiplied by the total area which was dA naught will be equal to the final intensity, which is dA times I prime. Now I prime will reduce by by the cosine term, or the intensity will drop by cos theta. So what you see here, the scattered radiation that you will see will be attenuated by an angle theta. So what you have here, if the angle theta is small, the reflected uniform scattered radiation is more, since cos theta will be close to 1, and when theta is close to 90 degrees, the radiation or the scattering is minimum, since cos theta at 90 is equal to 0. Please note that the scattered radiation is independent of the viewing angle. Due to the angle theta, a beam of light dA naught is spread over a dA, so that uniform scattering reduces by cos theta. We call this the Lambert's cosine law. The ideal diffuse surface reflect according to the Lambert's cosine law, which states the energy reflected by the small portion of of a surface from a light source in a given direction is proportional to the cosine of the angle between that direction and the surface normal. These are often called Lambertian surface. Note that the reflected intensity is independent of the viewing direction but does depend on the surface orientation with regards to the light source. So here I have got the light source is maximum when theta is equal to 0, that is making an angle 0 with the normal, where cosine theta is equal to 1, and it is minimum when theta is equal to 90, when cos theta is equal to 0. So computing the diffuse reflection, the angle of reflection, angle between the reflectance normal and the incoming light is the angle of incidence. So here I have got the angle of incidence, and it is uniformly diffused in all directions, shown by the light blue color intensity. So I diffused lambda is equal to kd lambda time kd lambda being the property of the surface, and I light lambda cos theta. And cos theta can always be written as a dot product of the normalized vector L and N. So I have got cos theta is equal to N dot L. So the equation changes accordingly. So here I have got the equation for diffused intensity. The directional light source, the same scene lit with a directional and an ambient light source, is shown here, and this is the direction of the light source hitting the sphere. Please note that the angle close to the surface center here is basically incidence in the beam is incident at here. The angle is close to 0, but as this parallel beam hits this surface, where since it's a surface, the normal to the surface is changing, and because the normal increases as it moves away from this spot, and therefore the intensity of the illumination reduces by cosine theta. And here you see, because of this variation of illumination, you get the shading of the object. In the previous case, this sphere looked like a flat circle. Now it shows a three-dimensional surface because of the shading effect coming due to the cosine scattering or the Lambertian surface. So here I have got now the third term added to my equation of intensity. So I is equal to Ke plus Ia Ka plus Id Kd cos theta. Same thing, I could write it with the dot product. What you see here below, again, there are sphere with being illuminated from different direction. Here I show you by the arrow the direction at which it is being illuminated, and you see how the shading of the sphere changes by the direction of illumination. The diffuse lighting, we need only to consider angles between 0 and 90 degrees because it's cos theta. Angle above theta is equal to 0, so I can take from plus 90 to minus 90, but the terms which is 0 to minus 90 is similar to the terms which is from 0 to 90, the cosine function being symmetric over this area. So it is sufficient to take the angle between 0 and 90 degree. A Lambertian surface seen at several different lighting angles is shown below. But apart from this, the light reaching this Lambertian surface may get attenuated due to the distance from where it is traversing. For instance, if the light source is at a distance dl, the attenuation, because the light source being illuminating in all directions uniformly, will reduce by the Gauss's law by inverse square law. So the F attenuation, or the term I could multiply to the intensity, could be 1 upon dl square. If we consider dust particles on the path and there is some scattering which takes place from the light and there is an attenuation due to scattering, we may further add an e to the power minus sigma dl term there, where sigma being the scattering cross section, and because of the scattering cross section some amount of illumination is lost to other directions. In graphics, sometimes one uses an equation of this kind. F attenuation is equal to minimum of 1 upon a quadratic equation C0 plus C1 dl plus C2 dl square, where C0, C1 and C2 are coefficients which can be varied depending on the attenuation that we would like to compute. Please note that this has no physical relevance. This is just a hack and to produce an attenuation. The first two attenuation has a physical significance. Maybe to explain it as an exponential may be difficult. Therefore, a quadratic equation of this kind may look simpler to compute attenuation. Now, point light sources. Earlier we had taken the assumption that the light source has to be parallel, but now since I have modified the equation so that I explain the equation as a dot product, and I could sort of now integrate the illumination over the whole beam by doing a dot product between L and N, N being constant while the L vector is varying for a diverging beam or for point sources, and therefore again you could easily integrate over the surface to get the illumination accordingly. So it is not difficult to compute for point sources, only that it is little more complicated and it has a little more mathematics in computing the diffused illumination. So here are effects of a spotlight, where you see these spheres are being illuminated by a point source or a cone of beam, and because of this you see that there is occlusion, and because of occlusion you have these black spots in the shadow which is forming out of the occlusions of this thing. The spotlights are point sources whose intensity falls off directionally, requires color, point, direction, fall off parameter, and this point source is of course supported in GL. Other lighting sources, area light sources define a 2D emissive surfaces, usually a disk or polygon. That is, you have an extended light source. A good example is a fluorescent light panel or a tube light, for instance, which has got an extension in one direction, capable of generating soft shadows. So here you will see that there will be that two types of shadows forming because of the partial occlusion of the light source or full occlusion of the light source. So you may have, wherever you have a full occlusion, you have a full shadow, which you will call it the penumbra, and the other one where you have got partial occlusion as the ambra. So you have got the ambra and the penumbra which occurs due to this illumination. We will come to these sort of effects at a later stage. Next, we come to objects which are shiny objects. We see that due to this, there are shiny objects, there is a shine that occurs that makes us feel the object is extremely well polished or the object is rough. So the shiny surface exhibits a specular reflection, polished metal or a glossy car finish that you see here. So here I have got two images of one of a diffuse lighting, and the same thing is you add a specular lighting to it. What you see is a bright white spot which occurs here over the normal diffuse lighting, so which makes it look, apart from us making it look like spherical, it gives us an effect or a sense of the texture of the object and tells us that the object is polished, maybe metallic, or it has a glossy finish. A light shining on a specular surface causes a bright spot known as specular highlight. Where these highlights appear is a function of the viewer's position, so the specular reflectance is view dependent. Now, up to now, what we have seen is that we had the direction of light source was important. So placing the light source in the world coordinate, I could create the illumination equation. But for specular illumination, I need to place the camera. I need to know where I'm looking at. So depending on my position, how close am I to the reflected direction? If the object was an ideal mirror, the light would have reflected in a particular direction, that is the same angle that it makes to the normal. The incident beam makes to the normal. In the opposite direction, the same angle is followed by the reflected beam. This is from the laws of physics. And how close are we viewing to this reflected beam angle is what is important in generating the viewing dependency, and therefore a viewing dependency comes into the equation. So the physics of reflection at a microscopic level, a specular reflection surface is very smooth. This ray of light are likely to bounce off the microgeometry in a mirror-like fashion. The smoother the surface, the closer it becomes to a perfect mirror. So if the surface is absolutely smooth, it's an ideal mirror, then the whole light reflects as a perfect mirror in a particular direction. But if it is not a perfect mirror, it reflects in all directions. Now coming to the optics of reflection, using the reflection that follows the Snell's law, the incoming ray and the reflected ray lie in a plane with the surface normal. The angle that the reflected ray forms with the surface normal equals to the angle formed by the incoming ray and the surface normal. The angle that the reflected ray forms with the surface normal equals the angle formed by the incoming rays and the surface normal. So here I have got the normal, the L is my incoming ray, which is at an angle theta L, and the reflected beam is at an angle theta R, and the Snell's law tells us that theta L is equal to theta reflected or theta R. So here I have got the the reflection is strongest near the mirror angle. You see here the light being illuminated and the angles being the same. So let us try to derive the reflected beam from the angle L and the normal N. So we know that theta L is equal to theta R. So if I take the projection of L on the normal, I get a term called cosine theta n cap. Since L cap and n cap are normalized coordinate, so I'll have the cosine theta n cap would be the component of the vector L on in the direction of n. Now, if this is cos theta n, this we can easily write as a dot product of n dot L in the n cap direction. Now, of course, I can break the vector L into two components. The other component being perpendicular to the normal, that is on the surface of the illuminating surface, and this can be written simply by doing L minus the component that is the perpendicular component or the component parallel to the normal. So L minus n cap dot L cap times n cap. Now the reflected beam, we see that this beam is in the other direction, and it is the negative of this component. So I'll have minus L plus n cap dot L n cap, and if this is the component along the surface, the perpendicular component remains the same, n dot L times n cap, and if we add both these terms, I get a relationship of the reflected beam, which is effectively depending on n cap dot L times n cap minus L plus n cap dot L times n cap. This could be simplified and written as 2 times n dot L times n cap minus L cap. So the non-ideal specular reflection, Snell's law applied to a perfect mirror-like surface, but aside from mirror and chrome, few surfaces exhibit perfect specularity. So what you have is a macroscopic roughness in the surface, and because of this macroscopic roughness in the surface that you see in this figure, the scattering, though the beam is coming in a particular direction, it should scatter at an angle opposite by an angle theta, but due to this variation in the roughness, the ray sees different angles around the incident beam angle. And because of this variation in these angles, there is a spread in the reflected beam. Now the reflected beam is no more just in the direction of the reflectance of an ideal mirror, but occupies, maximum is in that direction, but occupies a softer radiation around it. So how can we capture the soft reflections of the surface that are glossy rather than mirror-like? One option, model the microgeometry of the surface and explicitly bounce ray for it. This is doing complication. Basically, go take a tunneling microscope, see the roughness of the objects, study the solid state surface of the object, and based on that come up with a scattering law, or take a simple approximation and say that it has a favored direction, but it is sort of spreading around that favored direction. So non-ideal specular reflectance and empirical approximation. Hypothesis: the most light reflects according to the Snell's law. But because of microscopic surface variation, some light may be reflected in a direction slightly off the ideal reflected ray. The second hypothesis is, as we move from the ideal reflected ray, some light is still reflected, but there is a strong attenuation. It is not uniformly in all direction, but there is certainly a sufficient amount of radiation in other direction. So here you see a non-ideal specular reflection and empirical approximation illustrated. So here I have got a ray L hitting at an angle theta. It should have reflected in the direction r, but instead of reflecting at a direction r, it sort of reflects in multiple direction, which is centered or co-centered with to the direction r. So here you have the effect, a beam hitting the surface which is being spread over this area. How might we model this fallout? You see, this is a drastic fallout. You see here the angle, the intensity rises highly and then falls out heavily. Now this is sometimes called the Phong lighting. Most common lighting model in the computer graphics was suggested by Phong, and this is the equation or the empirical relationship of this specular lighting. So here you have got the property of the material Ks times I light times cos phi to the power Nshiny. Now what is cos phi? Cos phi is the phi being the direction between the reflected beam and the viewing position. So now when we fix the camera, we can compute the direction v, and once we have the vector v, we can find out cos phi as the dot product between r and phi. Of course, I don't know direction r, but I know where the light sources are and I know the normal to the surface. So I have already calculated the vector r in function of illumination and the normal to the surface, and through which I can always generate r. The Nshiny term is purely empirical constant that varies the rate of fall off through this model. Has no physical basis. It works sort of in practice. So it's totally a mathematical formulation. Please don't try to find physics into this relationship. So if I plot this function phi as a function of Nshiny for different values of Nshiny terms, so this diagram shows how the Phong reflectance term drops off with the divergence of the viewing angle from the ideal reflected ray. So here you see the green curve, which is for n is equal to 10, and as n reduces, this concentration of the beam, the more thinner, the pencil-like specular Phong illumination reduces, And we see at 1 it follows a normal cos theta term, and if we take n less than 1, we practically get a uniform illumination, which is shown with the yellow curve. So effectively this term of the Phong lighting reduces to the previous Lambert's radiation, because when I take ns equal to 0.1 or 0.001, I will have a very flat illumination that is similar to the Lambert's illumination that we have already seen. So here you see how these angles, this is taken the figure 14 from the book Hans and Baker, showing this variation of this intensity with the angle phi. So calculating the Phong lighting, the cost term of the Phong lighting can be computed using vector arithmetic. So I've got I specular, which is equal to Ks lambda times I lighting lambda multiplied by V dot R Nshiny lambda, where V is the unit vector towards the viewer or the camera direction. R is the ideal reflectance direction, and so cos phi is equal to V cap time dot R cap. So here you have got a V cap dot R cap to the power Nshiny lambda. Please note that Nshiny could vary with lambda to get other effects. That is having the effect of the specular light, which has got a color dependency, and this color dependency will come if n is different for different wavelengths altogether. Generally what we have seen, the specular part is white in color or having is uniform for all illumination, but it may not be true. It can be, we can illuminate it for a particular angle and it will work best for that particular angle. So here I have got the equation of the specular lighting, which is given here, and here you see the illumination or the light. If I plot the intensity in which is being reflected, the maximum is centered at the reflected beam. Of course, I'm watching it from V, so I will not see the maximum, but I will see a particular direction here. This will be the intensity observed by me, by the object, and this looks pretty realistic. So here I have got a specular reflection. A mirror like surfaces will reflect in this manner, where I have got a lesser incident beam and a more incident beam, which is showing this reflectance. The same thing in the specular lighting would be spreaded out, and partial mirror like is common, and where I will have this spreaded out illumination, which is given here. So V here is the direction of the camera. So the Phong example, these spheres are illustrate the Phong model as L and Nshiny are varied. So combining everything together, we will have a simple analytical model. I'll have a diffuse reflection, a specular reflection, I will have an emission and the ambient light. If I combine all of them, this is the picturesque or graphical model of illumination, showing all the types of illumination which have been considered for this model of illumination. So I have a diffuse reflection, a specular reflection, and an emission term and an ambient term. Of course, I may need not have the emission term for every point of my graphics. This emission term will depend on the points which are itself the light source. Of course, when I have an emission term, it will not at all, the other terms will practically become zero in the process. So here I've the angle of incident has changed, and due to the change in the angle of incident, you see that the ambient radiation has reduced, and the specular reflection is again also changing and becoming much more sharper. OpenGL Reflectance Model, the sum difference specular emissions and ambient is shown here. So you can generate this this table where you have this combination of these different intensities which are used in GL to model the surface. So there are inbuilt functions in GL to generate. We now come to the final combination equation for a single light source. So here I have got a point here. This is my light source, and I have my viewing position here. This is my normal, and this is my reflected direction. The angle is the same, theta theta, and this angle between the reflected beam and the viewing angle is phi. So here I've got cos theta is equal to n cap dot L cap, and cos phi is equal to V cap dot R cap. Of course, when I represent it in the equation below, the caps are understood. So in the equation below, I have, as you see, that Ke has been replaced by IE. It is one and the same thing. Ke was chosen because it was specifically the property of the material, and therefore since I'd chosen K as the property of the material, but since this term is both the light source as well as the material, we can choose either Ke or IE. It is one and the same. So here I have got I is equal to IE plus the ambient term Ka plus IAL, where Ka is the ambient property of the surface and IAL is the ambient light. I have got Kd multiplied by n dot L IL, my third term. This is the Lambert's scattering, homogeneous scattering in all directions. Here the direction of light is important, but the direction of the position of the camera is not important. Then I have the fourth term, the specular term, in which the direction of light as well as the direction of viewing is important, where you see I have got a Ks term multiplied by a V dot n to the power n, V being the direction of the camera and R being the direction of the reflected beam or the reflected beam times the IL. Please note that the third term and the fourth term have the same IL because a light source in the second term is the same light source in the fourth term. So here I have got this equation where, supposing if I have now, instead of one light source, I have multiple light source as it is shown here. I've got one viewing angle, so I will have this summation. As you see here, this summation where the light source is written with an index Li, and II being the intensity of the light source which is illuminating it. So here you have got a reflected beam. Each source will have a different reflected beam incidence, so which will be a different Ri depending on Li. So here I have got this equation is modified, and a summation term is added for multiple light sources of this equation. Coefficient review. We have seen this equation. The different coefficients of this equations are lambda, the wavelength, I, the light intensity which we are modeling, K is the material specific which defines the color of the material. It's a material specific constant. E, emissivity, A, the ambient component, D, the diffused component or the Lambert's component. N is the normal to the surface, the vector normal to the surface. L is the vector towards the light source from the surface. So if I know the coordinates of the light source and I know the point on which it is illuminating, I can always generate L, the vector L, and the normalized vector L by dividing the vector by its modulus. S stands for the specular component, the shine component. R is the reflection vector. The reflection vector is according to the Snell's law, where the light hitting the surface at an angle theta with the normal reflects in the opposite direction by the same angle theta. So the vector R has already been determined in function of L and the normal vector, which we will be using. V is a vector towards the viewer or the camera. That is, if I know the position of the camera, I can always calculate compute the V vector from the position XYZ of the object which is being illumined. And N stands for the Phong component or the shining component, that is the exponential component, and this depends on the material that is being used. So let us see this in a figure again. We have already seen the diagram, the way the illumination has taken place, but let us revisit the diagram here. So here I show you that I have an object which is a cylinder, and there is a light source shown by the bulb. A ray of light hits a position in the 3-dimension which is defined by x, y, z, and the light, using the Snell's law and the normal, if I draw the normal to this surface at the point x, y, z, this is the normal to the surface, and if using the Snell's law, it reflects at an angle, same angle on the opposite side. This is the reflection angle if the surface was an ideal mirror, and the blue vector is the camera angle. So what we are planning to do is that this angle here is phi, cos phi, which was written as a dot product of r vector and the visual vector, needs to be modified and written in function of L and the normal vector n. We have done this calculation. If you remember this slide on geometric reflection, we had found out the component of L on the normal vector, and this component is nothing else but cos theta I times the normal vector, which can be defined as n dot L n cap. And similarly, we can determine the other component of the L vector by subtracting the component in the direction of normal. And in the same way, we have computed R, the reflected coefficient, and the reflected coefficient thus computed is given by this equation, which is simplified to this equation. Now what we have is that we have this equation, the final illumination equation, and in this equation the R component will replace it by this vector, so that we have all the components of computation. And if we do replace this vector, this is the final equation that we get. As you see here, that the term which is under the power n has changed by the second vector, and this gives the final illumination equation which we will use. The summation of light is due to multiple light sources that you will encounter with. We have seen that we have used illumination for shine part, but we have seen materials like silver, gold, or dielectric glasses. They suddenly have high amount of reflectivity at angles close to 90 degrees, which the cosine theta function does not provide. Here we replaced by the cosine theta function by a function of this kind, where you have an angle where you see, for this is empirically determined, where the attenuation, suddenly there is a rise in reflectivity at angles close to 90 degrees, which you see in this material. So while designing materials of silver, gold, and dielectric, this sort of a function may be used. This is from figure 14-15 of Hans and Baker's book. We have said that slowly we are trying to compute things as close to the reality as possible. Discontinuity meshing has been used here to determine a light source. Here, as you see here, the light source is not a point source but a triangular source, which we have determined by 3 vertices: a yellow vertex, a blue vertex, and a green vertex. Now each of these and we have an occulter, or an object which is blocking the light source, and this object is a rectangular, a cuboid. Now if we join the edges of this object with the 3 edge points of the source, we get 3 levels of shadow, which is shown by the yellow square, the green square, and the blue square. Each of these squares represent the 3 corners of the source of light, and the intersection of all the three surfaces is the ambra, and the union of all of them is the penumbra, which is formed for an extended source. So limit of ambra and penumbra captures nice shadow boundaries, complex geometric computation. The mesh is getting complex. So here we have a scene which has been computed. Here you see that we have multiple light sources, extended light sources, and due to these extended light sources, you have multiple shadows, ambra and penumbra, that you see here at different locations below the table and under the chairs. And this image, the blue lines highlight these different shadows which have been computed. Gibson in 96 had computed done such a computation, and such computation took time of 1 hour 57 minutes. This work has been further improved with visibility skeleton and discontinuity meshing, and now this computation takes about 10 minutes 23 seconds. Of course, it is an extreme improvement from the work of Gibson, but still it is not in real time, and such high amount of computation cannot be used in gaming graphics. But of course, we can use it in movies while generating graphics for the movies, because the images are generated and used offline. For instance, this light source here now has a direction in which it is hitting these objects. Now, because of this direction of light source, the shadow and the surfaces are having different properties. Now, as I move the position of the light source, you see the shadow of the objects change position to different regions and different. I see the effect of the shadow at different regions. The panther at the background, you see the shine on the panther. It reflects light towards the camera and creates a shine, showing that it looks like a metallic object. Similarly, I have here a bell which is metallic, which then reflects this beam, and therefore I see the shine in the middle of this bell which is there. But for instance, if I take this piece, this acts like a mirror, and you see the shine, the lamp directly focusing on the camera. It acts like a mirror. So basically what you see here is the direction of the reflected beam. If it falls onto the camera, it reflects more light. Now if I change the angle of this object, you see the intensity varying on the camera or the direction that you have. So it depends on the reflected beam, and now I can also see the light. This is a proper reflection. Same thing if I take a metallic object and do the same, I do not get a similar, I think it is much more clear. I cannot see the lamp on this metallic object, but I see the shine. This specular shine becomes very sharp when it is a perfect mirror. As the smoothness of the reflectance diminishes, this sharpness reduces and this direction becomes broader until I get a very rough surface, say for instance the cube, where it creates, it's a pretty rough, so it doesn't reflect as much as the brass container reflected, and it produces a term which of course depends on the angle at which I am reflecting light. Now here you see that the red is being flatly illumined by the light source. Now I change the light source to an angle which is perpendicular to it at 90 degrees. Here you see the blue surface of the Rubik's Cube here seem to be more illumined. The red has changed to a different color. Again I bring back the light on the red. You see the intensity varies with the angle of incident. Now the angle is absolutely 0 degrees. That is, the lamp is behind the camera, and as I move the angle, increase the angle of incident to 90 degrees, the intensity drops and I practically see it as a shadow. I don't see. With this, we end one of the most important topics of illumination. We have seen how light is an important aspect in finding out light and shadow and creating a three-dimension of the object that we see. And the laws of physics, though we are not making use of it, how through an empirical hack we manage to represent the animation, represent the illumination as close to the reality as possible.